Good day, class. Let's look at Kirchhoff's laws and how we're going to use those um, in our circuit analysis. There's some these are some fundamental tools that you'll use. So um, uh, it's very powerful. So I would encourage you guys to uh, memorize or go through several applications using Kirchhoff's laws. And it's this analysis is primarily based off of two different thoughts here. Well, three if we talk about Ohm's law. But if we look at, and you'll see in just a second, if we look at a junction where we have wires going in and wires going out, so let's just say that we have this point at which we have current going in and out of a node, or a point where wires can be attached. It's NODE. What we're going to be doing is we're going to be summing all the currents in this area. And the sum of all those currents, maybe we call this I1, maybe we call this I2, and maybe we call this I3. It's going to add up to 0. But for our purposes, and this will be some I equal 1 to 3 just for purposes here. But for our purposes, we're going to need to recognize the sign of these. So it might be a little easier for us to think of I1 as negative I1. Sorry, positive I1 since it's going into the node. And then I2 and I3, we'll think of those as negative because the current is leaving the node. And all those are going to be thought to be equal to 0. So let's just look at a schematic of a circuit here. Let's see what we get. So let's build this circuit where we have a battery and a resistor. Here we'll see a node that attaches to this resistor. These appear to be in parallel, but we won't be able to solve it based on just that. And we'll have another resistor down here. So let's focus in on this thought of having nodes and what's going on at the node. Let's first start at the node and describe the current. And in some cases, we may not know the direction of the current. Typically, where we have a battery, where we have positive and negative, our conventional thought is our current is going to flow in this direction from negative to positive. It'll go across this resistor, go through this wire, and into this node. So let's call this I1. And then at this point, this junction point or this node, we'll call this node 1. We're going to have sort of a split of the current. So there's going to be some current that may want to leave in that direction and some that's going to want to leave in that direction. So remember, this was current I1, and maybe we'll name this as current I2, and this will be current I3. So as this current continues through this wire and through that resistor and into that node, it is still current I3. And as this current goes through this wire and through this resistor, it becomes current I2. So the way to think of this is for each one of these nodes, N1 and 2, we'll figure out how much current is going in and how much is going out. And we'll see that essentially their their equations, their mathematical equations are going to be the same. So let's look at N2. So N2, we're going to be summing all the current. So we're using Kirchhoff's junction or current law. So you'll sometimes see it KCL. By doing this, we'll know that this is equal to 0, first off. Sum of all currents at a node or a junction adds up to 0. And then just simply look at the direction of the arrows is the easiest way of thinking about this. Going out, we're going to think of that as negative current, I1. Coming in, it'll be I2 and I3 as well. And then you'll notice that a lot of these currents are the junction rule, or the sum of all the currents are going to be basically the same mathematical equation. So the sum of all the currents at node 1 over here is going to be, let's see, coming in, well, let's set this equal to 0. So coming in, this time we have a positive I1, and we have negative I2 and I3. But mathematically, these two are essentially the same. They just differ by a minus sign. So we're just going to choose one. So we'll just choose this equation here just because the lead number has something that's positive, and it just makes it a lot easier for me. Okay. Second thing we're going to do is we're going to look at what's going on inside each one of these loops. And so if we consider this as our first loop, maybe we might decide that we're going to analyze everything in this direction. And likewise, we might do the same thing in this loop as well. Call it L2. And the directions that we choose for L1 and L2 are arbitrary, meaning it's just completely a guess. Directions are arbitrary for L1 and L2. So it's completely a guess. We're gonna go in this direction. It's random, and so it's also a guess that our current is going in this direction across the resistor and out this node. It may be quite the opposite. Um, so we'll make corrections for that later on. At the end, we'll see what happens if need be. So the second rule that you're going to want to look at pertains to our voltage rule. And the voltage rule is a little bit more, I don't want to say complex, but we got to do a little bit more work with that. So I'm going to come back to this picture in just a second. And let's remind ourselves how Ohm's law works. So Ohm's law basically said that our voltage is equal to our current times the resistor. And so when we go across various components, to begin with, we're just going to be moving across batteries and resistors. So when we go across, let's start with a resistor. So we first need to know the direction of our current. And so let's just say that our current, let's see, we had this current here across this resistor, and we called it I1. and we deemed that across this current, or across this resistor, um, it was moving to the right, if you will. Now there's going to be a voltage drop across this resistor. And you'll see in just a second where we may have to look at it from a different perspective. Now, we're going to couple that with the direction of our loop. So what does that mean? That means that as we go around this loop, maybe we'll start here. We're going to look at basically 1, 2, 3 components in this loop. This is going to tell us which direction to flow in as we try to pick up what's going on. So let's see here. So we'll have that we're going to rotate in this direction. So let's pretend that we've gone across this battery. The battery's a little bit easier. So we have a current that's moving to the right because we chose it that way arbitrarily. And so there's going to be a voltage drop. Now, how much is the voltage drop? The voltage drop is going to be, we'll call it V1. It's going to be I1 times that resistor. And let's call it for right now R1. Call this R1. So there's going to be some voltage drop, which is going to be negative for us in just a second. Now, let's just say that for purposes of this example, we decided that our current still goes in the same direction, I1, but we decided to analyze the loop in the other direction. That means L1 would have been going against the direction of the current. So in this case, there's going to be, when we analyze this, there's going to be a voltage increase. When we do our math, right? So we have to couple that with the loop direction. And in this case, let's just call it L1X, just so we don't get it confused with anything. All right. So there's going to be some voltage increase, I1 times R. And this will be some negative amount that you'll see in just a second. Now, when we look at the voltage drop across a battery, the voltage drop across a battery is going to be either it'll be given to us or it'll be implied to be either positive or negative, but we have to look at the battery symbol. So when we have a negative slash positive battery symbol, there's going to be a voltage gain in this direction. Relative to the loop, again, if the loop is going in that direction. So in our case, what we're going to do is I'm going to put some numeric values in here. So for our purposes, the battery is going to have a 4-volt increase in this direction. And then first resistor is going to have a 10 ohm resistance. That'll be a voltage drop. We'll call this one R2. It'll have some resistance. We'll call that 20 ohms. And then R3 down here at the bottom, we'll say that that is 50 ohms. So one more time, so as it relates to the battery, as we go in this direction relative to the loop, right, we're going to see a voltage gain of 4 volts. We go all the way around, the sum of all voltages are going to equal to 0. So let's press that in as well as we analyze this circuit. So we're going to press together the current rule, and at the same time, we're going to look at the voltage rule as we analyze this. So a little bit more room here. If we sum all our voltages, and we're going to remember, we're going to start, let's look at loop 1. They're going to add up to 0. And I like to start at a node here. So nothing relative to a voltage drop is going to happen. So we'll go through the wire, and we can see that there's a voltage gain. We're going in this direction. We're going clockwise. So there's a positive increase of 4 volts across that battery. Across this resistor, there's going to be a voltage drop. So what's the voltage drop? Well, we don't know the current. That's what we're going to be trying to figure out. So it's going to be a negative I1 times R, and we know R to be 10. We continue around the loop. We see we're going in the same direction as the current. So we're going across this resistor. If the current were going in the opposite direction, there wouldn't be a voltage drop. There would be a voltage gain. And so, but in this case, there's a voltage drop of negative, use Ohm's law, I2 times that resistance of 20. So we have this equation. Now for loop 2, let's just do it a little bit differently because, well, actually we'll be fine here. For loop 2, I wanted to integrate the fact of going against the current across a resistor to show you what happens when we get a voltage gain across a resistor when we calculate it. So for loop 2, let's do our voltage rule. And we haven't forgotten about this current piece, this piece right here. We'll come back to that in just a second. All right, so loop 2. We'll start at a node. I like to just maybe start in the top left corner here. Sum of all voltages in loop add up to 0. But this time we'll notice that we're going around this loop, but we're going against the direction of the current. So against the direction of the current across a resistor invokes a voltage gain. And so the voltage gain is going to be positive the current, which is I2 in this instance, times the resistance of 20. We continue around, we follow this pattern, but then again here we're going across this resistor in the same direction as the current. The loop travels in this direction, and so there's a voltage drop. These could be a little tricky, so you gotta stay focused on the direction of the loop relative to the direction of the current. And so the voltage drop there is going to be times 50. There is no battery in this circuit, this part of the circuit, and so this will be all that we're left with. So you'll notice here in total, we have 3 unknowns, I1, I2, I3. And they come as a byproduct also of this. If we have 3 unknowns, we need 3 unique equations. And so going a little faster here, first equation from the node piece of this, the junction rule, we have that I1 minus I2 minus I3 is equal to 0. We picked one. From the voltage rule, we'll put these kind of in a cleaner descending order, if you will. So negative 10 I1 minus 20 I2 is equal to negative 4. Just put the constant on the other side. And the third equation comes from loop 2. We have no I1, so we'll have 20 I2 minus 50 I3 equal 0. So here's our system. So our system now can be solved multiple ways. Probably the easiest way to solve the system is to use your graphing calculator, or if you're not familiar with or don't have a graphing calculator, you can use um, the simultaneous equations where I'll show you how to add these up in just a second. So on your calculator, you're going to want to, see if you can see my screen here. Well, we're going to probably need both of these to show up at the same time. And I'll share with you a link um, in terms of how to do this even without a calculator. There's all kinds of built-in formulas out there to solve simultaneous equations. So just hang tight here with me. But on our calculator, we'll go into the matrix mode. I'm using a TI-83, so you'll hit second function and then x to the negative 1. Right, so second function x to the negative 1. And then we'll create an equation, I'm sorry, a matrix. And I called it, we're under the names subtab, and I called it A. And we're going to want it to be a 3x4 equation. So if you don't have it set up that way, you'll have to edit it. Okay. Go over to the edit mode and you just type in 3, enter, 4, enter. We're essentially going to put this where we pick off the coefficients. So we'll have 1, -1, -1, 0, -10, -20. There's 0 here, and -4 for that row, that column, 0, 20, -50, and 0. Okay, so I went on and entered those numbers in here. It's a little hard to see, but each time you hit enter a number on this calculator, you'll hit enter and it'll move you to the next component or the next cell in here. And so what you're going to want to do now is you're going to want to put this in reduced row echelon form. So essentially, you're going to want to put this on your calculator so that it looks like zeros above the diagonal and ones below the diagonal. Our answers are going to be A, B, and C. So how do I do that? I have to, it's a little bit clunky here, so I have to go out and I have to go back into the matrix area. And this time I'm going to go over to the subtab that says math. It'll say math up here. And then I have to look for this one that says RREF. So RREF. I want to print that out on my home screen. And then, probably just a little clunky, I have to go back into matrix and I have to type in or hover over the number 1 or whatever number corresponds to your matrix and then hit enter so it prints it on the home screen. You can do that as well on the home screen, but it's a little faster this way. And then now my next button is going to tell me my answers. So A turns out to be equal to 0.165, and this is going to be in amps. B, or I2 is equal to 0.118 amps. This was I1. And then C, or I3, is equal to 0.047 amps. And so that's how you'll solve these problems. If you get answers that are negative, you get a negative current flowing through these. And remember, the way we set this up is we said that our our loops and our direction of the currents are arbitrary. Current direction arbitrary. That means you can choose whichever direction you want. If you get a negative current, you just switch the direction of the current that you chose. So if you got something, and let's just say that you picked that the current for I2 was going this way, you just simply flip it so that it goes in that direction. So if I2 is equal to some negative number, change direction in schematic. Okay. And same thing for all the other ones, I1, I3, so on and so forth. Current direction that you select is arbitrary. Loop direction that you select is also arbitrary. Don't want this video to be too long. We're pause, and I'm going to get you the link for the other site for simultaneous equations. Okay, so here is the site, one site that I found. I'm sure there's others. There's probably tons of them that allows you to solve a system of equations. You're simply just gonna plug in whatever the numbers are. We had, you know, 1, 2, 3, 4. We had 12 different components that we have to plug in here. So you just plug it in, and it should allow you to set up the number of equations that you need. So pretty easy, pretty straightforward. Hopefully this will help you. If you have any questions, feel free to email or give me a call. Take care.